Hi everyone. This video is an introduction to section 14.5 on the chain rule for functions of several variables. Let's start with a quick reminder of the chain rule in the single variable setting. Recall that the chain rule tells us how to take the derivative of a composition of functions. So if we want the derivative of f composed with g, we get f prime of g of x times g prime of x. So we take the derivative of the outside function f, leave the inside function alone, and then take the derivative of the inside function. Now when I teach calculus, I always use this comic by Courtney Gibbons to help my students remember the chain rule. She encourages you to differentiate the mother, leave the baby inside, and then differentiate the baby. Now there are several versions of the chain rule for functions of more than one variable. Let's start with the simplest case. Suppose z is a differentiable function of two variables x and y, where x and y are differentiable functions of a single variable t. Then z is a differentiable function of t, and the derivative of z with respect to t can be found by taking the partial derivative of z with respect to x, multiplying by the derivative of x with respect to t, and then adding the partial derivative of z with respect to y times the derivative of y with respect to t. As a quick note on notation here, notice that because z is a function of two variables x and y, when we take the derivative of z with respect to x or y, these are partial derivatives. However, since x and y are functions of the single variable t, when we take the derivative of x or y with respect to t, these are single variable derivatives, our regular old dz dt and dy dt. Let's look at an example. Suppose z is the function 3x squared y plus 4xy cubed, where x is cosine of t and y is sine of 4t. Let's find the derivative of z with respect to t when t equals 0. Notice z is a function of two variables x and y, whereas x and y are functions of the single variable t. To find the derivative of z with respect to t, let's start with our formula. So, for dz dt, we start with the partial derivative of z with respect to x. So the partial derivative of z with respect to x is 6xy plus 4y cubed. We multiply by the derivative of x with respect to t, which is negative sine of t, and then add the partial derivative of z with respect to y, which is 3x squared plus 12xy squared, times the derivative of y with respect to t, which is 4 cosine of 4t. Now we're asked to evaluate this derivative when t equals 0, but we cannot simply replace our t's with 0. We have other variables to consider, the x and the y as well. Since x is cosine of t and y is sine of 4t, we note that when t equals 0, x is cosine of 0, which is 1, and y is sine of 0, which is 0. So, evaluating when t equals 0, x equals 1, and y equals 0, we see that the derivative of z with respect to t simplifies to 12. Here's a possible interpretation of this problem. Recall that x was cosine of t and y was sine of 4t. dz dt is of course the rate of change of z with respect to t. As the point xy moves along the curve c with parametric equations, x equals cosine of t, y equals sine of 4t. You see a picture of that curve on the screen. For example, if z is a temperature function, if z gives the temperature at the point xy, then our derivative dz dt will give the rate at which the temperature changes as that point moves along this parametric curve. Here's a second version of the chain rule. Suppose that z is again a differentiable function of two variables x and y, but this time x and y are also functions of more than one variable. So suppose x and y are both differentiable functions of the variables s and t. Then we can take the partial derivatives of z with respect to t or s. These formulas look very similar to the case 1, except that since every function is a function of more than one variable, then every derivative is a partial derivative. Let's do an example. If z is sine of x times the cosine of y, where x is st squared and y is s squared t, let's find the partial derivative of z with respect to s. We begin with our formula. So to find the partial derivative of z with respect to s, we start with the partial derivative of z with respect to x, which is cosine of x times cosine of y. We multiply by the partial derivative of x with respect to s, which is t squared, and then add the partial derivative of z with respect to y, which is a minus sine of y times sine of x, and finally multiply by the partial derivative of y with respect to s, which is 2st. Now, rather than leaving our answer like this, where we have a lot of variables x, y, s, and t, we can clean this up by replacing x with st squared and y with s squared t. So let's do that. So this would be our final answer for our partial derivative of z with respect to s. Now, one way to visualize the chain rule is with a tree diagram. Here's how it works. Suppose z is a function of x and y, and that x and y are themselves functions of s and t. Then we can draw what we call a tree diagram. Here we go. So z is a function of x and y, x is a function of s and t, and y is also a function of s and t. Here's our formula for the partial derivative of z with respect to t. One way to remember this formula using our tree diagram is to think of all the possible ways we can start at z and end at t. I'll highlight them here. So from z, we can go through x to get to t, or from z, we can go through y to get to t. Here's our other formula, the partial derivative of z with respect to s. So let's map out on our tree diagram all the possible ways we can start at z and end at s. They're highlighted here in orange. So from z, we can go through x to get to s, or we can go through y to get to s. Let's see this tree diagram in action. Let's write out the chain rule for the partial derivative of w with respect to a in the case that w is a function of u, s, and t, where u, s, and t are each functions of a and b. So first, let's create a tree diagram. W is a function of u, s, and t. U is a function of a and b. S is a function of a and b. And t is a function of a and b. Since we want the partial derivative of w with respect to a, let's highlight all the ways we can start at w and end at a. Here they are. So using our tree diagram, we see that for our partial derivative of w with respect to a, we can go from w through u to get to a, through s to get to a, or through t to get to a. And so our tree diagram helps us then write out the formula we'll want to use to compute the partial derivative for w with respect to a. If we now had equations for these functions, we would use this rule to compute our actual derivative. That's all for our introduction. Thanks, guys.